Assalamu alaikum everyone. Today we have to start the section 8-8 of your book, which is about the flow rate and the velocity measurement, and this one is the last topic of chapter number 8, and it is very interesting, and we will see that how we can use the flow measuring devices to measure the volumetric flow rate and even the velocity of a fluid in the pipelines. So we will be using some of the concepts that we studied in the chapter number 5 about using the journal energy equation, and then we will use some of the ideas that we studied in the chapter number 8 earlier. So let's see what we have here. So let's start with this one, flow rate and velocity measurement. A major application area of fluid mechanics is the determination of the fluid flow rate, and numerous devices have been developed over the years for the purpose of flow metering. Flow meters range widely in their level of sophistication, size, cost, accuracy, versatility, capacity, pressure drop, and the operating principle. Okay, so these flow measuring devices they differ in terms of sophistication, size, cost, accuracy, and these are the other things. We give an overview of the meters commonly used to measure the flow rate of the liquids and the gases flowing through the pipes or the ducts. So we will study in this section that how we can measure the volumetric flow rates of the liquids and the gases in the pipelines and in the ducts. We limit our consideration to incompressible fluids, so we will only talk about the incompressible fluids, mainly the liquids. So we know what is the equation for the volumetric flow rate. It is the volumetric flow rate can be equal to velocity times cross-sectional area. So we can have the value for the volumetric flow rate. Measuring the flow rate is usually done by measuring flow velocity, and many flow meters are simply velocity meters used for the purpose of metering flow. Okay, so what we are going to do here from this explanation, that if we measure the velocity of a fluid within this pipeline, having the information about the cross-sectional area, we can actually estimate the value for the volumetric flow rate. So let's see what we have here. We talked about the pitted and the pitted static probes earlier in chapter number 5. So we will just review some part of this one because we are going to use this one again here. Pitted probes, also called as pitted tubes, and pitted static probes are widely used for flow speed measurement. So these pitted tubes, we talked in chapter number 5 that we can use these pitted tubes to measure the velocity of a fluid within the pipelines. A pitted probe is just a tube with a pressure tap at the stagnation point that measures the stagnation pressure, while a pitted static probe has both a stagnation pressure tap and several circumferential static pressure taps, and it measures both the stagnation and the static pressures. So this one is a simple pitted probe, and this one is a pitted static probe. Now in the pitted probe, we can see that there is only one hole at the tip of this pitted tube, from where we can measure the velocity of a fluid in the pipeline at a certain level. Okay, so we can move this pitted tube up and down in the pipeline to get the velocity of a particular layer of a fluid, and we know that at the tip of this pitted tube, the velocity of the fluid will become equal to 0, and the velocity head will be converted into the pressure head. So this point, we can call this one as a stagnation pressure. On the other hand, we can have the pitted static probe. Now in this probe, we see that there are two holes, one at the inlet at the tip of this pitted tube, where we can measure the stagnation pressure, and then we can have certain holes on the circumferential of this tube, okay, from where we can measure the pitted from where we can measure the static pressure. Okay, so we can link these two pressures together by using some manometer to get the value for the delta P. Now what equation did we get earlier? We can have this kind of situation. This one is the pitted static probe. So here we can measure the stagnation pressure, and here we can measure the static pressure. Now when we put this tube in the pipeline and we apply the assumption on this journal energy equation, what we got here, at the tip of this pitted tube, what should be the value for the pressure? It should be the maximum value for the pressure, that is P1, that is the stagnation pressure. On the other hand, at the circumferential of this tube, we can have the low value for the pressure, which is called as a static pressure, that is represented by P2. So P1 here represents you the stagnation pressure. Then in terms of Z1 and Z2, there is no height difference here, so we can remove this part. And then what should be the value for the V1 and the V2? V1 is a velocity at this point and V2 is a velocity at this point. So at this point, what we see here, the fluid will come into contact with the with this petri tube, and the velocity of the fluid at the tip of this petri tube will become 0. So V1 will be equal to 0, and V2 velocity we need to calculate. Okay, so we can remove this V1 and we will rearrange the equation in terms of V2, that is equal to V. Okay, so this is the equation that we got earlier in chapter number 5 also. So how we can use this equation? This equation is used to measure the velocity of a fluid at a given point in the pipeline. P1 represent you the stagnation pressure, P2 represent you the static pressure, and density represent you the density of this fluid that is in the pipeline. That can be water or any fluid that you are dealing with. Now let us see that how we can use certain types of obstruction flow meters. So this one is a typical example of the obstruction flow meters. We can have orifice meter, venturi meter, and the nozzle meters. These are the typical meters that you can see in the industries. So why do we call this one as an obstruction meters? Flow meters based on this principle are called as obstruction flow meter and are widely used to measure the flow rates of gases and the liquids. Okay, so these meters, because we put some kind of obstruction in the direction of the flow, so these meters are called as obstruction flow meters. For example, here we have this pipeline here, and then we attach some kind of orifice plate here. So what is this orifice plate? So let us see what this orifice plate looks like. So this is a picture that I googled online. So this is a typical orifice plate. Okay, so how you can attach this orifice plate in the pipeline? You can have this kind of arrangement. So this orifice comes with a different arrangement. Sometimes it is having only one hole in the center, sometimes it is having two holes, or maybe you can see some orifice meter that have the holes like eccentric holes or the segmental holes. Okay, so what is the function of this orifice meter? That it will reduce the pressure in the pipeline, and that pressure drop can be measured with the help of the manometer. So if we have the if we can use this equation for the manometer that we use here, so P1 minus P2 that we get from the pressure drop, and then we can use this equation to get this velocity. So let's see here. So for example, we have this kind of orifice meter that we attach on the pipeline. Okay, this kind of orifice meter that we attach on the pipeline. So we can have this kind of arrangement. So point 1 it represent you the complete diameter of the pipeline or area of the pipeline, and point 2 represent you the area for the flow of the fluid within this orifice meter, right? So now we apply the assumptions on the general energy equation or the Bernoulli equation to simplify this equation and to get the value for the velocity. So what we see here, if we use the equation for the mass balance, so the volumetric flow rate at point 1, it should be equal to the volumetric flow rate at point 2, right? So we can have this equation, volumetric flow rate at point 1, it should be equal to volumetric flow rate at point 2, and then we can rearrange the equation in terms of V1 velocity, and then we can write the area in the form of diameter. So V1 can be written in the form of V2, having some information about the diameter. So this is the first equation that we get in terms of the velocity. Then we can use the general energy equation or the simplified Bernoulli equation, and we apply the assumptions on this equation. So the height at Z1 and Z2 it is equal, so we can remove the height factor from here, and then we can simplify this equation in the form of V2 velocity. So what should be the velocity at the point 2? And this equation we get here after the rearrangement of this equation, and in this equation we have introduced this new term which is beta. So what is this beta? It is the ratio of the smaller diameter to the capital diameter. What is the smaller diameter? It is the diameter of the obstruction flow meter, and capital diameter, it is the diameter of the pipeline. So we can rearrange this equation to get the value for the velocity at the point 2, and in terms of smaller in terms of this ratio of smaller d to capital D, we can write this one in terms of beta. Okay, so once we have the value for this V2, that is the velocity at point 2, now we can actually calculate what should be the volumetric flow rate at the point 2. So we can multiply the V2 with the cross-sectional area of this orifice meter to get the value for the volumetric flow rate. That So we can get the value for the volumetric flow rate, that is our aim. So we multiply the velocity of a fluid within this small cross-sectional area of the flow measuring device, and we multiply this one with the velocity of the fluid from this equation, and we get the value for the volumetric flow rate. Now, the losses can be accounted for by incorporating a correction factor called as the discharge coefficient CD, whose value, which is less than 1, is determined experimentally. Okay, now depending on the type of flow measuring device we are using, we can use the orifice meter, we can use the venturi meter, we can use the nozzle meter. I can show you the figures here. So this one is basically the orifice meter. Like this one is the plate that we install in the center of the pipeline, having the smaller diameter of the orifice. This one is an example for the flow nozzle. Now you look at the construction of this meter. You can have like two slits of the iron maybe or stainless steel that will cause some pressure drop in this pipeline. And then you can have the venturi meter. Now if you look at the construction of this venturi meter, this is gradual contraction and gradual expansion. Now what you can see here in terms of the pressure drop, if you simply look at the figures here, what you can see that in terms of the orifice meter, you are suddenly dropping the pressure of the fluid within the pipeline, right, using this orifice plate, depending on the smaller diameter of the orifice. So you can have the maximum pressure drop in the orifice meter. Now if you compare the orifice meter with the flow nozzle, what we see here, like the construction of this flow nozzle, it is more sophisticated compared to the orifice. So you can have like a deflection of the fluid within this flow nozzle, and you can have a slightly less value for the pressure drop compared to this flow nozzle. Now the third one, which is a venturi meter, what we can see here, there is a gradual reduction in the area of the flow, and then there is a gradual expansion of the flow, right? So the area is reducing here and then it is expanding here. So what we see here in this venturi meter, there will be very less value for the pressure drop compared to orifice meter and the flow nozzle. Now we can compare these kinds of the flow measuring devices in terms of the discharge coefficient. Okay, so the meters that can cause very less pressure drop, they can have the very high value for the discharge coefficient. The maximum value for the discharge coefficient is 1. So the value 1 represent you that there is no pressure drop due to this equipment. But if the value for the discharge coefficient is low, maybe for this orifice meter, which is 0.61, you can have the very high value for the pressure drop. Okay, so we will see these values. So let's see what we are studying. So the losses can be accounted by incorporating a correction factor called as discharge coefficient CD, whose value, which is less than 1, is determined experimentally. So we have to introduce a new factor which is called as the discharge coefficient. So what is this discharge coefficient? It represents you the pressure drop caused by a certain flow measuring device. Okay, so if you look at these equations, here we calculate the velocity at the center of this orifice meter, and then we multiply this one with the cross-sectional area to get the value for the volumetric flow rate. So we will use the same equation here to get the value for the volumetric flow rate. So the value for the velocity that we will use here, this is the value for the velocity that is here, and then we multiply the velocity with the cross-sectional area of the flow measuring device to get the volumetric flow rate. So this is the equation, final equation that we get for the volumetric flow rate for the suction flow meters. Now the value for this CD, it is different, and it depends on the type of flow measuring device that you are using. Now what is this A naught here? Can you tell me, or can you have a guess? What is the value for this A naught? It represents you the cross-sectional area of the flow measuring device, which is which is the 0.2 in this orifice meter. Okay, so this A2 here, it is basically the area of the suction flow meter. So every time that you will use this equation, A naught represent you the cross-sectional area of the flow measuring device. Okay, not the area for the pipeline. And the beta here, you can see this one, it is a ratio between the smaller diameter to the capital diameter. Smaller diameter represent the diameter of the flow measuring device, and the capital diameter, it represents the diameter of the pipeline. The value for the CD depends on both B and the Reynolds number, and charts and curve fit correlations for the discharge coefficient are available for various types of obstruction meters. Okay, so sometimes we get the value for this CD directly from the vendor. If you are having the orifice meter, what should be the value? If you are using the nozzle meter or the venturi meters, most of the times we are directly provided the value for this discharge coefficient. But if the values are not provided, then we can use some correlations and the curve fit correlations to get the value for the discharge coefficient. For example, for the orifice meter, we can have this equation to get the value for the discharge coefficient, in which you need to have an information about the beta, which is the ratio of the smaller diameter to the capital diameter, or the diameter of the orifice or the flow measuring device divided by the diameter of the pipeline, and you need to have the value for the Reynolds number. Okay, and the same way we have an equation for the nozzle flow meter, so you should have the value for the beta and the Reynolds number. So if the value for the beta it is greater than 0.25 and less than 0.75, and the Reynolds number lies between these two ranges, then we can have this information. For flow with the higher Reynolds numbers greater than 30,000, the value for the CD can be taken as 0.96 for the flow nozzle and 0.61 for the orifice. Okay, so if you are getting the value for the Reynolds number between this range and the beta value between this range, then the value for the orifice meter, it should be 0.61, and in case of nozzle meters, the value can be 0.96. Now one information is missing here about this venturi meter. The drag coefficient or the CD value for this venturi meter, it is around 0.98. Okay, the value for the discharge coefficient for this one is very high, which is give us the information that the pressure drop that is caused by this venturi meter would be very less compared to these two meters. Okay, so here you can find out the values for the orifice meter and also for the flow nozzles. For the venturi meter, the values of the discharge coefficient, it is 0.98 that you can use in your examples and in numericals. Now let us solve this example that will conclude this chapter. The flow rate of methanol at 20 degrees C, the density is provided and the viscosity is provided through a 4 centimeter diameter pipe. So the diameter of this pipeline, it is 4 centimeter, is to be measured with a 3 centimeter diameter orifice. The diameter of the orifice that we attached here, it is 3 centimeter, 3 centimeter orifice meter, equipped with a mercury manometer across the orifice plate, and we attach this manometer across this pipeline. If the differential height of the manometer is 11 centimeter, determine the flow rate of the methanol through the pipe and the average flow velocity. Okay, so this is a situation. We attach some kind of orifice meter on the pipeline that caused some delta P in the pipeline, that is measured by using a mercury manometer, and we got the value for the height here for the mercury manometer, that is 11 centimeter. And now we are supposed to calculate the volumetric flow rate of the methanol through this pipeline and the average flow velocity. So what we can do here, first of all, we can use the equation of the manometer to get the value for this delta P. So what equations did we use? So let's see this one. So the equation for the delta P that we can use here, rho for the mercury minus rho for the methanol GH. So we have been using this equation since chapter number 5. So we will get the value for the delta P. Now this beta here, that is the ratio of the smaller to the capital diameter, 3 by 4, that comes out to be 0.75. Then the cross-sectional area for the orifice meter, A naught, you can put the value for the diameter, and the A naught comes out to be this one. Then you can use this equation for the volumetric flow rate to get the value for the overall flow rate through the flow measuring device. Now this equation, I told you that how you can derive this equation by yourself by using simple Bernoulli equation and just like rearranging the equation and using the fact beta here. So you can get this equation quickly by applying some assumptions on the general energy equation or the Bernoulli equation, or you can directly remember this equation. Okay, so this is the equation that we can use for the volumetric flow rate. In terms of delta P, you can use In terms of delta P, you can use this equation for the manometer. Density here, it represents you the density of the fluid that is in the pipeline, which is methanol, multiplied by 1 minus beta 4, which is the ratio for the diameter of the orifice divided by diameter of the pipeline. So you can reading the equation and you can simply plug in the values that is given to you in the question. And the value for the volumetric flow rate, it comes out to be 3.09 into 10 raised to the power minus 3 meter cube per second. So this is the value for the volumetric flow rate. Now here you can also see that the discharge coefficient for the orifice meter, the value is 0.61. Okay, so this one is the journal value. So this one is the journal value that we get from here, 0.61 for the orifice, keeping these two conditions satisfied. Okay, but the value for this orifice or the flow measuring device, it can be slightly changed when we change the vendors. Okay, depending on the construction and the pressure drop caused by these orifice meter, these values can be slightly changed. So we have to do the iterations to get the exact value. But as a good estimate, we can start with the values that is provided in the literature. So here we use the value for the discharge coefficient to be 0.61, and then we get the value for the volumetric flow rate. Now we need to calculate the value for the velocity as asked in the question. So we divide the volumetric flow rate with the cross-sectional area. Now which cross-sectional area we are using here? We are using the cross-sectional area of the pipeline. Now you have to see in the question here. Okay, the average flow velocity, we have to determine the flow rate of methanol through the pipe and the average flow velocity. Okay, so it is written that we have to get the value for the volumetric flow rate and the velocity in the pipeline. So the velocity that we will calculate here, it should include the area for the pipeline that is asked in the question. If it is asked that what is the velocity in the flow measuring device, then you have to use the area for the or the diameter of the orifice. Okay, so for this one, velocity in the pipeline, it comes out to be 2.46 meter per second. Now what we can do here, we have used a value for the discharge coefficient given in the literature 0.61, but this is not the exact value for the given example. So what we need to do here, we have to calculate the value for the Reynolds number. The value for the Reynolds number, it depends on density, velocity, diameter and the viscosity. So you will put the values here in this equation to get the value for the Reynolds number. That comes out to be 1.32 into 10 raised to the power 5. And then we will use the equation for the orifice meter to get the value for the discharge coefficient. Okay, now you will put the values for the discharge coefficient here. Beta value you can get from the ratio for the small d to the capital D, and the Reynolds number that you just calculate here. So you will put the values here in this equation to get the new value for the discharge coefficient for the orifice. Okay, now what we have seen here, earlier we used the value for the discharge coefficient to be 0.61, but if we are using the equation for this orifice meter, we will be getting new value for the discharge coefficient 0.601, which is slightly lower than the value that we used earlier. Now for this new value, what we can do, we can use this new value in this equation again to get the new value for the volumetric flow rate and to get the new value for the velocity. And then again we will calculate the value for the Reynolds number that can be used in this equation to get the value for the new discharge coefficient. So we can do these iterations again and again till the point we get the same value for the discharge coefficient that we used in the problem and the value that we get from this equation. Okay, now once we keep on doing these iterations, what we see here, the new value is 0.601, which differs from the original gas value of 0.61. Using this refined value of discharge coefficient, the flow rate becomes 3.04 liter per second, which differs from the original result by 1.6%. After a couple of iterations, the final converged flow rate is 3.04 liter per second, and the average velocity is 2.42 meter per second to 3 significant figures. Okay, so what we see here, we can start with the journal value for the discharge coefficient provided in the literature, and then we can refine our results by doing some iterations using the equation for the discharge coefficient for the given flow measuring device till the point that we get the same value between the CD that we are using here and the CD that we are using here. Okay, so at this so once you get the same values for the discharge coefficient, the value for the volumetric flow rate and the velocities, these can be reliable. Okay, so I hope this lecture is very easy, and just we have to deal with this small equation, and you can derive this equation by the way very easily. Okay, so you can derive this equation by yourself, and let me know if you feel any difficulty. So with this example, our chapter number 8 will be finished, and next time we will try to solve some examples and exercise questions of the chapter number 8. Okay, so I hope you enjoyed this chapter, and this is one of the most important chapter after chapter number 5 that is used in the industries to calculate the pressure drop, volumetric flow rate, and the velocities. Okay, so just practice this one and let me know if you feel any difficulty. Okay, thank you everyone.